Hi, guys. Today we're going to finish up our notes on 10.2 and also go over section 10.3. So we talked about liquids before and how they relate to kinetic molecular theory, which is the theory that everything is made out of these little atoms and molecules that are constantly in motion. We talked about how they have a relatively high density because liquids are all touching. When we compare them to gases, which are very far apart and separate, they have a much higher density than gases. So greater mass per unit volume than a gas. They're relatively incompressible because, like we can see right here in the little water, the molecules are touching, and if you put them under pressure, they could become a tiny bit closer together, but really the amount of space in between them, since they're touching, can't be decreased very much, not like a gas, where we can easily compress a gas. And they have the ability to diffuse. So some of you might have done, some of you did do the extra credit of adding food coloring to hot and cold water. And you might have seen that in the cold water, the dye just sinks to the bottom and kind of sits there, and it takes a long time. And in the hot water, when you add the drops, the dye spreads out very quickly. And that is because that's showing us the difference in the temperature of the water molecules affecting the kinetic energy or the speed, the velocity at which those water molecules are traveling. So the hotter the water, the faster they move and the faster the dye spreads throughout. The colder the water, the slower the little atoms and molecules are bumping into each other, and the slower that um, dye is going to spread out. Okay, eventually both of them will end up like this picture where they're all completely mixed evenly. That is diffusion, one liquid mixing into another. We can also have diffusion of gases like our air freshener sprayed in the room. But this is a diffusion of two liquids. And they're going to mix completely because they are randomly and constantly moving in all directions. Okay, so they're bumping into each other. Eventually, they will totally spread out, and both the hot and the cold water will look like this. The hot water, it happens a lot faster, and the cold water, it would happen over a much longer time. Okay, so that's their ability to diffuse. Surface tension was the little net on top. So the attractions of surface molecules to each other that creates a little net on top of the water. Capillary action is water's ability to move up a thin tube because of its attraction to the side of that tube, which would be adhesion, and the attraction to other water molecules, which would be cohesion. Okay, evaporation and boiling we will get back to today. And we left off right here with formation of solids. So this is 10.2. We talked about all these things, and we have to write down the very last little bit, formation of solids. Freezing is a liquid changing to a solid. Okay, and we will also come back to this as well today. Okay, so that was the last little bit of 10.2. Today, we're actually focusing on 10.3, which is kinetic molecular theory, focusing on just the solids. Okay, so kinetic molecular theory, again, they're made of molecules that are constantly in motion. Solids, because they are all touching and they are fixed in their positions, they can only vibrate. Okay, so properties of solids. They are packed more closely than both liquids and gases, except water. Water is a very important exception where the solid is actually farther apart than its liquid, and that's why ice floats. Remember, we talked about that on Friday? What we need to go over are these very important types of intermolecular forces that hold molecules together, especially in solids. So, what is it that's holding them together? When you have a solid, like let's say NaCl, you have ions that are touching in this repeating crystal lattice pattern, right? What is it that's holding them together? So an intermolecular force we need to actually define. I'm going to squeeze that over here to the side. Inter, this part means between. Let me use a different color. Between. Molecular, just like it meant up here, means molecules. So these are forces between two molecules. So the force between the Na and the Cl would be an intermolecular force. More commonly, we have our little water molecules. Okay, so here's one water and here's another water facing the opposite way. And there's going to be a force of attraction that we draw as a dotted line in between these water molecules. This is my intermolecular force between two water molecules. Okay, another place you might have seen the prefix inter is like an interstate highway. It's a highway that goes between two states, so that's what that inter means. Okay, and we abbreviate intermolecular forces as IMFs. Okay, so there are a few types that we need to know. Type 1, these are London dispersion forces, or LDF, also sometimes just called dispersion forces. And that's a force that all molecules have. So everything has LDF, or dispersion forces. And it's because of a momentary displacement of electrons. So the common examples here with these LDFs are hydrocarbons. So if I have this long chain, remember glue kind of looks like this. If I have a long chain of carbons and hydrogens, every bend and point on this is a carbon. And if I have two of them stacked up next to each other, like in glue, there's going to be some attraction between them. Let's draw the intermolecular forces with blue. Okay, so there's some kind of attraction between these. And the reason that there's this force between these two long molecules is because the electrons are constantly moving around. The electrons go wherever they want on here. They're bouncing all over the place, moving up and down and side to side and everywhere. And at one split second, there might be more electrons on the top than the bottom. So that means that the top would be partially negative and the bottom would be partially positive. Okay, well, that for a split second causes this semi-polarity. It's called a dipole moment. Okay, that is going to cause the one next to it to also, then the electrons are going to kind of shift up towards the top here. So the top of the bottom molecule would be partially negative and then partially positive underneath. And so for that split second or fraction of a second, these two are going to be attracted to each other. And then the charges all balance out again because this long chain that I drew is actually non-polar. Remember things with just C's and H's, they're called hydrocarbons. That's going to be a non-polar bond. So the only thing holding them together would be that dipole moment, that very short momentary displacement of electrons. Okay, so that is called a dispersion force, or London dispersion force. And it only happens for a fraction of a second and then it goes away. And that's why most nonpolar things aren't held together very tightly at all. And that's why most of them are very volatile. Like think of propane and butane and hexane and octane. All of those are like gases at room temperature, or they turn to gases pretty easily. Like when you go and you put gas at the gas station and you smell that really strong smell, that's because they vaporize very easily because there's not a lot of forces holding them together. So these guys can escape into the air and then we smell them. Okay, so that's dispersion forces. All molecules have them. Every single molecule has dispersion forces. The second type of intermolecular force is called a dipole-dipole force. And dipole meaning two poles, so we have a positive end and a negative end. and we have two polar molecules, so dipole, dipole. It's the electrostatic, that's positives and negatives, force between polar molecules. So this one up here was for all molecules. Number 2, dipole, dipole is just polar molecules. Okay, so just polar. And a common example of dipole, dipole is HCl. Okay, this little molecule where I would have a little H and a big Cl next to another little H and Cl. So I have two molecules of HCl. There's going to be a force of attraction right here between these guys. Okay, so that green dotted line is not an actual bond. It's just a attraction of the negative end and the positive end on two neighboring molecules. So that is called dipole force. Okay. The third type is a very special dipole-dipole force, and it's called hydrogen bonding, which we've seen before. This should be familiar. Water has hydrogen bonds. Okay, so it's just like a dipole-dipole, except it's especially strong. And that extra strong dipole-dipole force gives water all of its amazing properties. Okay, so let's draw some little water molecules because this is where we see hydrogen bonding the most often. It also helps hold DNA together. Fun fact. Okay, so here's my oxygen on one water molecule. Here's another water molecule, and we'll draw a third water molecule up here. Okay, I gotta, of course, add the little hydrogens on there. So if the hydrogens are here and here on this water, that means that it's going to be attracted to the oxygen on this neighboring, and this one's going to be attracted. And so the hydrogens will be pointed the opposite way up here, and they would be attracted to some other water that's nearby. Okay, so the dotted lines that I drew are hydrogen bonds. They're a special, extra strong type of dipole-dipole force where H, those are my little Mickey Mouse ears, is bonded to, it can be bonded to F, fluorine, O, just like we have in water, or nitrogen as well. Okay, so the dotted lines that I drew here are hydrogen bonds. They're the bond between the partially positive hydrogens and the partially negative oxygens on neighboring water molecules. Okay, it is a very confusing name. A lot of people make the mistake of thinking that the hydrogen to the oxygen in the water molecule is a hydrogen bond. Very confusing name. Somebody chose a really poor name for these. But the bond between the H and the O in the molecule, that would be an intramolecular force, which you don't need to know. But the hydrogen bond that we're talking about is actually between two different water molecules, not in the same molecule. Okay, and the last type is called ion dipole. And it's the force between an ion, like Cl minus, for example, and a polar molecule like H2O. Okay, so if I draw a little water next to that chloride, since he's negatively charged, the positive part of the water is going to point towards him. And then I'll draw the dotted lines in green this time. So this force of attraction right here, this is the strongest type of intermolecular force because dipole, dipole, these were partial charges. That's what this little weird symbol, this lowercase delta, is a partial charge. Up here, this is totally negatively charged. So it's a complete charge. So we have a partial positive on the little hydrogens and this negative charge of the chloride. Okay, so this is an ion, that's the chloride, dipole, that's the water force. Okay, and we have different types of crystals that we need to know about in the solid section of the chapter. A crystal is a repeating pattern. It has a nice, beautiful, orderly repeating pattern to it. So think of a salt crystal or a crystal of quartz. They're very pretty. They're organized. They make the same shape. So a salt is going to always be cubic. Quartz, I believe, is a hexagon shape, but they have this nice orderly pattern. An amorphous, a meaning without, morphous meaning shape. So these don't have a shape. They're very random. And glass is an example of an amorphous. Oh, that's real ugly. Glass is an example of an amorphous solid. And that's why when glass breaks, it doesn't make nice regular shapes. It makes all kinds of random patterns and shapes and edges because it's an amorphous solid. Okay. Last but not least, solids have a definite shape and definite volume. So over here, when we were looking at our diagram, solids had definite shape and definite volume. Okay. They have high densities and they're incompressible because they are touching, just like our liquids were touching. So they have a high density. Usually, solids have a higher density than liquids, except with water's case. And they have a definite melting point, meaning that once you reach that melting point, for example, when water reaches that 0 degrees Celsius, or 32 Fahrenheit, when it reaches that temperature, there's enough energy to break the bonds between the little water molecules that were all perfectly lined up, like so. So when these reach 0 degrees, they have enough wiggle energy to break all of the hydrogen bonds that are holding it together and melt. Okay, and we will pick up there tomorrow. I am adjusting the schedule a little bit, so we will go over that in class tomorrow. I hope you guys have a wonderful day. Take care. I'll see you later. Bye bye.